Welcome everybody, and thank you for all turning out at 9 o'clock after the football game last night, for those of you who are following it. I'm going to do my obligatory kick-off a little bit about our project, which has kind of started this session, but generally the aim of today's session is more about the discussions. We've got a couple of talks to get us kind of thinking about things in the way we want to, but generally what we're here to do is to share some ideas, discuss topics that we think are relevant, with a mixed group where we have research infrastructure engineers who are building systems and research software engineers who are using them. So I'll start by saying I'm Helen Cooper. I work at the University of Surrey. I'm a research facilities manager, which covers both AI compute, but also things like audiovisual labs and robotics and all sorts of other bits and pieces for the People-Centered AI Institute. And my background was in computer vision as a researcher. So I helpfully took a segue sidestep at the point at 2012, which those of you who are AI integrated will understand is a terrible point at which to have stepped away from research, because that was when AI basically went, oh look, we can do this on GPUs. So the Asset Hub is about training up research infrastructure engineers. We are a UKRI funded initiative. We've got almost 4 million of funding to create training programs. It's about building those specialists who are maintaining and developing the digital research infrastructure that we all rely on. And we've teamed up with kind of groups like the BCS to see if we can make the training that we're doing something that will be recognised out in industry as well as within the academic environment. And this is all because what used to be HPC, mainly physics, a little bit of chemistry, that sort of thing, is now a huge influx of AI coming in, and it's lots more jobs, lots more GPU compute coming through, very different data patterns, very different workloads. But actually, one of the biggest challenges most areas are encountering is it's a very different user base and a very different attitude to coding. So the hub is made up of, Surrey is leading it, with Oxford, Bristol Imperial and Sheffield. It grew out of the JADE consortium that many of you will know, that was the GPU cluster that was hosted at Oxford. And the thing that I'm really going to shout about today is that we're running a mentoring scheme with HPC SIG for research infrastructure engineers. It'll be running from September to May, and it will be opening in July. And it's about, again, building connections between institutions, learning about things from other areas that do them differently, and building networks for those starting out in research infrastructure engineering or trying to build their careers within research infrastructure engineering. But also, if you're wondering about coming on board as a mentor, it's really useful for you because you will get training in how to be a mentor, how to coach, how to have those leadership skills and how to develop talent. So we'll be looking at doing a hybrid. We'll have structured support for people as part of the mentoring scheme, and there will be funding available for the mentor and mentees to meet up. Specifically, we're hoping to do a session at CI UK or around CI UK, and we'll be having funding so that you can attend that. So that's just a big plug for that if you're interested. And then I'm going to put this slide up. Just say we've got lots of interesting events coming up over the next few months. There's Richard Gillam from Isambard is giving us a webinar on the 14th of July about the differences that he's noticing on the Isambard system with agentic ops. Then we've got a hackathon coming up in September, which is going to be into Slinky. And that's a distributed hackathon. We're going to have teams in Surrey and teams in Sheffield, working on the same problem and connected digitally across the two sites. And we'll have a quick webinar before it for a bit of preparation. And then we'll have a co-design day. Those of you who haven't seen our co-design days before, they're about directing where the training for the hub is going to go, what's important, whether the training we're providing is what you want. And then on the 7th of October, There's been some work going on with some of the other RTP networks, which are looking at agile processes. They're mainly Scrum based. We're going to be doing an RIE based sessions, which is Kanban and agile for operations based teams, which is where the RIE teams tend to sit. And so that's all going to be available. So there's a couple of QR codes at the bottom. There's flyers on the front desk if you want to take away more information, but you can find out stuff about us there. And that's my sales pitch done. And at this point, I'd like to bring up Duggan to talk about software development from a RIE perspective, I think is.
Yeah.
The kind of area we're in.
Yeah.
So let me stop this, right?
Close the participants. That's thing as well.
Oh, okay. Right. Yeah, that would help. Make the slides bigger.
Whilst the slide deck is coming up, so for everyone in the room, my name is Duggan Withock. I'm head of research computing platforms at Imperial. My background was originally in astronomy at UCL many years ago, where I think I kind of moved into the HPC side as I don't know if anyone remembers the Miracle Consortium is one of the precursors to Dirac. So I was a support programmer for that. And over the years, I've kind of shifted around different institutions, Oxford, UCL, again, Warwick, and now at Imperial. Although, ironically, I probably live closer to the Cambridge HPC data centre than probably anyone in the Cambridge team does. Slide deck,
Yeah.
I can keep talking.
No, it's all right. It kicked me out.
You'll see that no.
So here we go. Presenting teams. There we go.
Thank you. Okay, so one other thing I think I want to start off with is apologies for the template of the slide deck. I think those of us who work at Imperial are not massively fond of the new color scheme, and we have a very basic logo now, so apologies for that. I think that's why some people are still using the old templates. So I'm kind of going to give it's kind of a talk, a kind of by all means interrupt me. I mean, I've been working on running in HPC systems for 20 years now, and through a lot of that time I've been building software for different sides of it. So at one point I was actually using it to run research for myself, but for many years I've also been supporting users in terms of building software. So I'm assuming we've got quite a mix of people in this room. So there'll be some people who are infrastructure engineers, some people are research software engineers, and so I've moved over from one side to the other many years ago. And if you're trying to use an HPC system, you often probably get a slightly you ask them to install, and it's different in every site, but you ask them to install a package for you, and you'll probably get occasionally a grumpy response of no, sorry, we can't do that. And what I want to do with this talk is kind of give you a little bit of perspective from what happens from the RIEs, in the sense of the things that we can and can't do, why we might ask you to upgrade things, why we might ask you to do things in a certain way. And hopefully, it might give you some insight to what happens on the back end as to the way things end up going. So I think I've only got 20 minutes to talk, and you might gather that I can ramble like anything. So Helen's going to probably throw things at me if I take too long.
Thank you.
Thank you.
Oh, that one works as well.
Yeah, there we go. So as I said, I kind of wanted to go through, you guys, those of you running scientific applications aren't doing the infrastructure sort of side of things, kind of give you a perspective of what happened, why the RIEs say certain things. Hopefully you'll get some insights and things that you might, if you are developing code yourself, might give you some insights on what you can do with the code to make it easier for your RIEs to actually deploy essentially. But also it's kind of going to hopefully spur some discussion on the way things are changing. Obviously, a lot of this is about AI now, and there's a big move to AI, and obviously it's already started, and where it starts becoming problematic for RIEs to do things centrally. So it's out of sync. Let me do that one.
Yeah.
Yeah.
Okay.
Okay. So there's a few topics on here. I won't talk through them. The one thing I will say though, so the slide deck I'm putting up here. So it was initially my bit of a brain dump and then followed up with support from colleagues at other sites, so Tina and Dean and etc. So what you'll see is our perspective of what our experiences are from our side. But if your local research infrastructure engineer says no, that's completely wrong, do what they say. It is really, they know their systems much better than we were ever going to know. So while we're trying to give kind of a broad generalized view on how things kind of happen, do what they say, because I don't want them coming after me if nothing else. But, it's always best to follow their advice over anyone else's. So first thing I want to talk about is full stack. So we have a lot of people who come and they've written a bit of code on their laptop. And they come to us on the cluster and it doesn't compile for one reason or another. And it's really important when you are building software in any kind of shape or form, and actually not even if you're only building software and you're running something, is that ideally it's important to think about the entire stack that you're running on. So everything from the operating system, scheduler, hardware. So Tina's doing a session on scheduler this afternoon. Hardware, interconnect, file system, all of this has an impact on how your application behaves, how it performs, and actually it can affect the maths that comes out of your code in the end. So anything down to changes in libraries on the operating system, down to differences in microarchitectures that your code is running on, can affect research outcomes. And it's painful because it means that maybe you need to make your code adapt to these different environments, different interconnects. So you're on Ethernet or you're InfiniBand, but when you go from one system to another, not just from your laptop, but from one HPC cluster to another HPC cluster, your code may produce different output because of any aspect of this stack. So it's really important to consider that whole range of those bits and pieces and why this might affect your research. And if you can, most HPC clusters have kind of an indication of what their system is built on, what operating system, whatever. It's good to kind of get some familiarity with that because that will help you in the long run. Now, we often get asked, we often get tickets that say I'm running sudo at install something or get something or other, and they go, why can't I do this? Well, okay, sudo's administrative command, but for many years sites have typically run Red Hat Enterprise Linux. Now obviously many of you probably run Ubuntu or something like that, some derivatives of it on your laptop or other devices, but you'll find that many HPC clusters still, although this is starting to change, run RHEL. And there are a number of reasons behind this, and a lot of it is historical, but a lot of it is also that if you're using an HPC cluster, it's going to have a number of highly specialized drivers for things like the file system, things like the network interconnect. And these will affect, what the vendor actually supports does actually limit what we can provide in terms of the file system, in terms of the operating system. So we've just put in a new cluster at Imperial. It's a high throughput cluster, it is Ethernet only. And we actually did consider putting Ubuntu on the system because it was more familiar for users and the environment that they got. But we ended up going for RHEL because Lenovo, NVIDIA, Weka, which are all these bits and pieces, gave better support for Red Hat Enterprise Linux, more reliable support for Red Hat Enterprise Linux than they do for Ubuntu. Some of this is around, in some respects, some of the licensing within Ubuntu stack, which affects what they can provide from the operating system, but also it makes it easier for the vendors to provide these device drivers for RHEL. And this is why you tend to find this, which doesn't necessarily match what you have on your own system. So I can't honestly remember what the slide deck is, so I'm winging this as I go along. So if we go from that and we go from the logical step of the operating system, we get to, well, a lot of people compile their software with something around GCC and a GNU compiler. And we get people coming to us asking, well, this software was working fine on CentOS 6. Why can I not compile it on CentOS 8? And there's a lot of there's been a lot of changes with compilers, and a lot of people have been reliant on slightly loose interpretation of things like C and Fortran, whatever. Modern compilers are much stricter than they used to be. They more closely follow the language standards, but also, it's actually quite difficult to get. It's not entirely impossible, but it's quite difficult to get a compiler running on an operating system that's older than the one that the operating system was built for. And if your code can't adapt to newer compilers, you quite possibly will not be able to actually get your code compiled using the one that's on the system if you can't use an old one. So as an example, OpenFOAM, I don't know if anyone uses OpenFOAM at all. It is probably a pet hate for some of the research infrastructure engineers. In fact, we had a ticket yesterday, I think it was, for OpenFOAM 2, which was released 15 years ago. Hasn't had any adaptations to modern compilers. It might compile. Actually, slight bits of it compile, but bits of it don't compile. And a lot of that is because nobody has taken the work to actually adapt parts of the routines to work with modern compilers. So you think, well, maybe we should push to GCC 2 or something like that. Try getting GCC 2 to work on Red Hat Enterprise Linux 8 or 9, as many sites are now moving to, or 10, as So it's important to think about this when you ask for the application. You ask for something old. It's quite possibly we can't compile it. If we do compile it, it might not actually run properly, might not give you the correct maths that you expect because things have changed along the way. It's important to think about this. It could be, as Tina reminded me, if your code is reliant on an old compiler, when your code is being compiled, if you use an older GCC, it won't understand your CPU that you're running on. It might revert to a fail-safe option, and if your code runs at all, it might be slow, or it might give you completely the wrong output. And this is fundamental. Even if you're doing Python workflows, a lot of your code is quite possibly being compiled with something like GCC at some point. So it's important to consider that kind of thing. 5 minutes, God, I gotta talk quicker then, haven't I? I told you I can talk. I do ramble, so I'm going to go quicker. Sometimes we do ask you to use a newer version of something. So, you gain OpenFOAM 2, please use a newer version of OpenFOAM because there's reasons nobody uses OpenFOAM 2 anymore. It could be security patching. It could be reasons within the code why, you should be using a newer version. Could be bug fixes that actually affects the maths of the outcome. We often find people ask us for a version of a code which isn't the hot fix or the patched version because it matches their output from 10, 15 years ago. There's a reason why it might have changed. But also, there's always this assumption if we ask you to use a newer version, it's not necessarily going to be any faster. There might be reasons why your code is taking longer to run now than it did previously. When you do compile your code yourself, think about where you are actually compiling it. Login nodes often, so a lot of sites don't want you to compile on login nodes because login nodes are typically shared between lots of users. Some of the more modern build tools are rubbish at controlling the parallelization. So you'll find some of the modern build tools, they go, well, there's 256 logical CPUs. We'll use all of them, and you'll have no opportunity to lock that down. So consider this when you're building it, and obviously follow whatever your local sites use. Now, there are ways of optimizing your code for the CPU architecture. So, some people will, we do this at Imperial. We have separate builds of software depending on which processor it's running on. And you can get this with things like march equals native for GCC and -x host. But you do need to be careful because these can sometimes detect CPU features which then actually either over optimize your code or are fundamentally unsafe. So it's important to test your code when you do actually compile it. And benchmark your code, which I think I've got some. I actually got that in there. That's good of me. So when you do build your applications, it's good to try and make it easier to build. So we get somebody at one point has found a good way, and I open up honest whilst we're going through this. I'm a terrible programmer, so I understand why certain processes have ended up being followed. But I think, when we get tool chains where somebody's going, well, my a.out doesn't exist when I run this script, is you're not following particularly great programming best practice. A lot of if those of you who are RSEs in the room can obviously support those who are like programming as postdocs, postgrads, and that training kind of thing. But also, if you're developing your code on a system which you're relying on system libraries, you're relying on this and that, you're going to end up making your code difficult to port to somewhere else. So we get this quite a lot. We get people asking us, well, my code won't compile. Well, that's because you've specifically requested pointing to a Ubuntu library from 2004 or something like that. So, but when you do have your code, and even if you don't develop code, it's really important to benchmark your code, find a particular run which you're happy with, which you can repeat, gives repeatable outcomes. When you move between systems, try that. Don't always assume that the more calls that you give something, the faster it will run, because there can be overheads from internode communication, even within the system. So some systems behave different to others. So if your code is memory bound, consider undersubscribing the calls. It's this kind of thing. You have to think about different run patterns to get the best out of the system, and it's not always use as much as possible. And I've got 2 minutes left. Yeah. So if you are building tools, code yourself, you'll find a lot of HPC sites now use standardized scientific software build tools. 2 of the most common ones are EasyBuild and SPAC, as I've got up here. So we use predominantly EasyBuild at Imperial. I think they do it at Birmingham and a few other sites. I think Cambridge uses SPAC, but somebody can correct me.
Cambridge uses SPAC.
Yeah.
EasyBuild in Oxford as well.
Yeah. So these tools help build the entire tool chain. And means that we can try and build systems which are independent of the fundamentally of the underlying operating system. Makes it easier to build software when we're going between Ubuntu or RHEL or whatever operating system. If you are building software yourself, if you're writing software, consider. So it's relatively easy to put in a pull request to either of these build systems. Consider supporting it yourself, because if you want other researchers at your institution to use a code, if you do the pull request in there and they already use EasyBuild, you can say there's already an easy config for my package. Can you just build it centrally? And it will make the RIEs much happier. I'm going to talk quicker. Python. I mean, there's a lot to say about Python, but I will just skip over a lot of this. AI frameworks are a nightmare. They're making life quite painful at the moment. One thing I will say, which I think doesn't always get flagged up, Anaconda and Conda are not the same thing, and you are not necessarily licensed to use Anaconda. And we do ask that everyone go and check their institution to make sure. So I know Imperial, we're in the process of trying to sign the agreement with them, but I know a lot of institutions haven't done this. And if you're using Anaconda, you're quite, as a member of staff, as an employee, you're quite possibly in breach of their terms and conditions. I just throw that in there for support of the other institutions. And containers. Containers are increasingly common. We're seeing very complex workflows coming through. So sometimes it's easier if someone brings a container to us with the workflow already in it, all the packages, all the libraries in it, but it's not a perfect solution. It's good for some of the AI frameworks, and I'll talk just quickly about Docker, but these containers get out of date, and they can have security flaws in them if you don't keep them up to date. They might be built on older systems, might not support the hardware that you're running on, and the container structures themselves. So if you look at Aptainer has changed from compared to Singularity. You can end up with incompatibilities between your container images when you're moving between them. I will just finish very quickly. I've got faster and faster. I'm sure none of this is actually sinking in. We often get asked why we don't run Docker, and I think I got first asked this at Oxford in 2014 or something like that. Things are changing along with this, but Docker was never designed for a scientific computing environment. So while the containers themselves are essentially okay, they're designed for kind of a different security model than what we tend to have with HPC clusters. We have HPC clusters, we've got lots of users, that you don't trust running on the system, and you need to be able to keep the processes separated, etc. Docker, that's not what Docker was designed for. Essentially, it was really designed around having a workflow of developers over here passing completed workflows over to here to then get deployed to production on trusted, relatively trusted systems. So that's why a lot of sites don't run Docker. I will just say that obviously there's things like Kubernetes now, so and some sites are starting to run Kubernetes stack. So we've just got a Run AI from NVIDIA stack coming online, which is based on Kubernetes. And Dean's going to talk about Slinky. No, somebody's going to talk about Slinky, which is a Kubernetes plugin for Slurm, isn't it?
Slurm and Kubernetes. It's like a bridge between.
Yeah,
So
that's the next hackathon.
Right. Okay. Next hackathon.
Yep.
Yeah.
Happy?
Yeah, I guess so. Any questions?
Yeah.
I'll move now.
Thanks, Evan. So that was, as Duncan says, just a gentle walk. But as I say, these talks are designed to spark some conversations later. Our next speaker is Sylvie. So I get your presentation up more fluidly than we did Evan's.
I know. Thank you. So good morning, everybody. So Ellen kindly invited someone from this project to do a talk. So because I'm here today, I will give the talk on behalf of Chris and Saul. So Chris is lead of the project. He's from Cambridge. I'm from UCL, and Richard is from Bristol. So as everybody else, I will just give you a quick words about who I am. So I'm Sylvie Ramos. I'm a principal research infrastructure developer at the Advanced Research Computing Department at the University College London. In terms of background, I have a pretty change a bit along the career. So when I started after my degree, we didn't talk a lot about AI. It was there, but we didn't talk a lot about machine learning. And at the time, I remember having one of the lecturers saying that Netscape was the future. So just to let you know how far we are coming from. So in here, so I started as a researcher working in Fusion, then moved to work in big facilities, work a lot with control and data acquisition systems. Then I moved more to data management, and more recently, I moved to OpenStack, working in cloud computing, and now at UCL. So at UCL, I lead the Unified AI Services team. How I ended up there, I didn't know much about AI, but at the time I did know about Kubernetes. So that's why I was given this project. So that's why now we are a team of 4. When I started, I was the only one in the team, and now we are 4. So that's about me. Then let's talk a little bit about the project. So here, just a quick overview about what the project is. So the National Federated Compute Services Network Plus is an initiative that is meant to engage compute service users and providers who are focused on the 3 pillars of governance, technology, and community. And the aim is to develop a roadmap for a national federation of compute services to support the UK's digital research infrastructure. So there was 2 rounds. We had the first round, and this project was part of the first round. 13 was accepted, funded, and in phase 2, UCL also has a project from phase 2, working with Cambridge, KCL, and Bristol. More on the containers, Kubernetes, and trusted research environments. For this phase 1, we are part of this one that started in September. Well, phase 2 started at around December, January. So each project will produce a report. So we are mainly doing a feasibility study that will be published in end of July, and we'll be meeting a DOI as a good practice. And the idea is to produce a roadmap with some recommendation for a future potential implementation. So this is the title of our project, the AI Container Registry Feasibility Study. So here is a project team. So as I said, Chris Ensel from Cambridge is leading the project. UCL and Bristol, we are the co-leads, and these are the team members. So in terms of work packages, so we divided in a few work packages. Work package 1, which is more community engagement and trying to understand the requirements of the community. Work package 2 is more a landscape analysis of existing tools and technology, more focused on what we could call standard HPC, which is mainly standard scatter like Slum. Then we have the work package 3, which is about the technical challenges. So, and work package 4, which are the governance challenges. Then we have work package 5, synthesis and roadmap, and 6 is more proof of concept, is like a stretch. We will be mainly focused on the first 4 during this presentation. So in terms of activity, we have done quite a few activities around the past few months. There was, we have several NFCS conference. We started one with a kickoff in the Upton in Edinburgh. Then you have the first workshop, which was co-located with the HPC SIG. We had around 58 attendees, around 25 online. The audience was mainly sysadmin, infrastructure and resource providers. And we got a focus on what the user needs, operational concern, the portability of the software. The second workshop was at UCL, and was focused more on the trusted research environment, which is now becoming a very big topic. And here we had quite a good attendance, and the audience are mainly AI researchers working on TRE. So we have presentation, for example, from Paros AI from KCL and the Fridge project as well. Then we had the NFCS conference, workshop 3, that was held during the Iceberg AI Days. This workshop was more around open discussion. We didn't have a specific presentation, so we talk about authentication and authorization, containers via the traditional module share, hosting and governance. Then we have NFCS conference again in London this time, 6 and 7 of July, to look at what has been done by all projects. And then we have a workshop 4, so please save the date. We'll have some QR code at the end if you want to register. So please register. And then we have the final NFCS conference, 10 and 11 of September to close, which will be held in Birmingham. So that was quite a large community involvement. So work package 2. So this work was done by mainly Bristol. So in here we compare different registries to see with different criteria. Single sign-on, multi-tenancy, security scanning. Security is becoming more and more of a concern, especially with containers. Access controls, if there was a user interface, if we can run it on-prem, if you can store other artifacts than only containers, if you can store like Python packages, for example, if this is open source. And here that's a rate limit. For example, Docker has a rate limit. So in here, the conclusion, and we focus mainly on the Arbor, I will talk later why we think that the on-premise can be a good solution compared to commercial ones. So here, as you can see, it has a yes, except that it's only for containers and charts rather than for other software packages. So work package 3. So in terms of technical challenges, when you talk about containers, nowadays we need to think about what I call the traditional HPC that you have been working on for quite a few years, and how it works. So we do a login node, you can run a job using Slurm, for example, or other scheduler. But we can see more about Kubernetes. So why Kubernetes is becoming important, especially with AI. So Kubernetes initially was to run long-running jobs and making sure that is highly available, that is always running. So with AI workloads, we have two types of workloads. We have the inference endpoint, which is a long-running, where we have a REST API that call a model and then get an output. So that's why it's quite important. You can also use this with batch jobs. So it has a flexibility to do both. Also, the TRE, Trusted Research Environments, projects like Fridge, also focus on Kubernetes. So they have made a lot of work around Kubernetes. In terms of differences, so container engine, where we talk about Aptainer, it's pretty popular, but Bricks also use Podman, which is Docker without root, so you can use it as a user. It's also, you don't need a daemon, for example. In terms of format, so that's Podman uses standard OCI, which is per layer, while Aptainer receive, which is a single file. Normally we you get the container and you convert it to C format. I can explain the differences between the two. And then, as Durham mentioned, we can use Spark, Easy Build as build tools. I'm not a specialist, I would say, on this stack. So yes, keep it in mind if you have any question. I know more about on the Kubernetes side. On the Kubernetes side, we can have several container runtime as well. So you can have containerd, CRO, but you can have also vendor-specific one like the NVIDIA container runtime. So that is used for a better performance. Here we use the standard OCI per layer. So generally, we have like a base image. The advantage of having a base image that we build on top of that. So when we push that image, if you build on top of the base image, you just push the difference. And when you pull the difference. So that means you can save storage and you can save in terms of pushing and pulling time. So that's main differences comparing to C, for example. So this is we discussed about, I mentioned Arbor on-prem. So the idea was that having on-prem, in terms of push and pull, it's quicker if you have the correct network configuration than having offsite. That's the main reason. There are some techniques that can improve performance. For example, layers, as I mentioned previously. We can store the image first, so it's already on the node, for example. There are other strategies like some tools that allow to start the container if not all the layers have been pulled, if they don't need them. We also, in terms of performance and storage, we can also improve it by separating data model from the container itself. So it's smaller, you need less storage. But we need to have some work with research on how to do it. So here we need to, here that will be each site will have their own container registry, basically the idea. Network, it's important, as I said, because of performance. Storage as well, so to store all the images, how we'll be managing the storage. And obviously the authentication and authorization through my access ID. So the idea is to have it closer to the compute, as I mentioned, to reduce the boot time. So in AI, containers tends to be built several tens of gigabytes if we don't add the model within the container. Then using this approach, you can have a multi-site deployment. So instead of having, for example, a pull-through, you can have a replication policy when you replicate the container across a different site. And so you can have, it's more resilient. If there is an issue, you have higher availability. Obviously, all this comes with a cost, right? So in terms of infrastructure, well, you need more storage when you do replication because you are replicating containers. In terms of network, we need to see firewall, work on the best way to handle this in terms of security as well. So so we'll need to see the advantages and the disadvantages. 1 minute. So finally here, that's about governance. So the idea is we have a CI pipeline, and we can have, for example, if it's in GitHub, having a GitHub action that will create a container and will check before pushing it to the federated container registry, tagging, do a vulnerability scan, licenses, authorization, public vs user namespace. Public means that should we maintain and curate these containers, that will be again an extra cost if we need someone to do that, or each user having their own containers in the namespace that they build. In terms of pooling, so some sites are some specific security policy. So, for example, do they need to pass the vulnerability scanning? How often should we run the vulnerability scanning? Should we tag it? And should we able having some policy to avoid pulling images that have some vulnerability already in there, so don't pass the scanning? It also depends on the hardware type. So here is just a governance structure that we propose. So having a chair who takes the decision, package container manager, representation from each site, and the idea is to have a set of approved policies, but also user guidelines. So I think I finished now. Oh, sorry, that's this one. So here's the QR code that I mentioned. One is survey. If you could fill this survey, that will help us with the project. That will be very much appreciated. And this one is if you want to attend the workshop in July at Cambridge, please scan it and register. And I think that's all. I'm open to discussion later on, but there are some questions. So thank you very much for your attention. Thank you.
Thank you very much, Sylvie. So that concludes the formal part. I'm going to suggest now that people put their laptops away, because the next thing I'm going to ask everybody to do is some work. So let me pull this up. So we've got some discussion topics for this for the rest of the session. We've got about 45 minutes left in the session. There's 5 topics. You're not necessarily going to get to spend time at each one. In the room, we're going to have physical tables, and online we will do some Miro boards in breakout rooms. So I've put here for in the room the rule of 2 feet. I don't know if you've ever come across this before. Essentially, I want you to optimize your time. If you are standing or sitting around a table and actually you've got nothing left to say on the topic, or you're not kind of getting anything more from the topic, move on. Don't apologize, because that'll break the conversation that's going on. Just get up and move. It's not rude. It's just making sure that everybody gets a chance to talk about everything they want to on every table. So as I say, no hard feelings. If somebody leaves while you're talking, it's not that they're being rude. It's just that they've been at that table for a while, perhaps, or maybe the discussion isn't what they thought it was going to be. And cross-pollinate. Use your 2 feet to wander to another table. Take ideas that you've had from one table to another table. Keep the discussion flowing. I'm going to ask my hub team to act as anchors on the tables so that they're there and can kind of say, oh yes, we discussed that earlier, and they've got ideas. There's post-it notes and pens. Big ideas, write them down. At the end of the session, the hub leads will feedback kind of 2 or 3 key ideas from each table so that we can kind of hear what came out of the various discussions, even if you weren't able to make it to that table in the 40 minutes. I'll let people know when we're kind of at 10-minute points so that you don't all lose complete track of time. So you have a chance to move if you've got absolutely engrossed in a topic. Okay? Right. If you turn the piece of paper over on the table, I think table 1 is this end and table 5 is that end. You'll see some kind of starter questions, but if you've got other things that aren't included on those starter questions, do feel free, yep, to is that the right one? Yeah, Milton, yeah. Okay, so I'm going to go through in order on the tables here, and then Anna, I don't know if you were able to feedback from the online sphere of what the discussion was happening there. So hope that was all interesting. I hope you got to see more than one table and discuss with people on more than one table. I had a little bit of propagation of ideas, kind of saw it coming through, which was great. If I could get a feedback from Tina on the build systems and
we had trouble staying on course, sort of like, because you always veer off into the problems of Python. And the fact that nobody understands what the difference between conda, anaconda, and all of those things is, and things like that. And there was also some confusion about of what AI tool chains actually sort of like means in this sort of context.
Yeah.
It's,
the language is not defined around any of it, and there is no. I mean, I'm eagerly awaiting the landscape kind of work that has come out of the project that Sylvia was talking about earlier.
One of the main points, sort of like that came out of it, is that sort of in a lot of AI built tool chains, sort of like the things with PyTorch and things like that. It's just the rate of change and the permutations that you can have them in are just simply too big, too high, too whatever to run with a traditional model of sort of like you provide the thing and then people can use it, because it changes too much and people wanted too many different permutations, and therefore a central provision of it makes little sense. So sort of like people do it for themselves. Which then also led into a discussion of how the multiple ways that can go wrong, because how do you then know it actually works?
Which takes us back down to the responsibility table down at the other end. Yes, and so that speed at which the change is happening has drivers in certain ways and changes the behaviour. That's a really interesting kind of pull out of that. Elena, are you able to give us some feedback? You can try. I'm putting Elena a bit on the spot because she's non-technical. She's our project manager, but
conversation on how to particularly being managed. But I think some people have the idea of using containers that can host different, not just Python, but like R as well, like different aspects of what you'd expect users to have who are computer literate, I guess, versus very purely biologists.
So containers can support both HPC and AI workflows, whereas HPC is struggling to support the AI workflows and the users who don't understand it. That's an interesting kind of high level of,
Just to be able to accommodate for everyone's different requirements and needs.
That combinatorial thing again, and the speed,
it could be a good environment model. Talk about
talked about TUV a little bit.
Yeah, that was
Now
one
it's
of the
a
mentioned,
A
yeah.
bit more lightweight, but just native Python development.
What was that? TUV, was that?
UV
UV.
from Astral.
Ah,
Yeah,
okay.
it's Rust based, so resolving package dependencies is a lot faster than something like Ponder.
Yes.
It's not best quoted.
The other mention was the overload of a file system, is that correct? Like as mentioned, and one solution we mentioned was Aurora. Yeah,
Aurora.
that could be implemented, for example. But yeah, I think that was what I could gather anyway.
Excellent. Thank you very much, Elena. And sorry for putting you on the spot for a technical thing there. Twin, would you like to feedback on containers versus native HPC software?
So actually, generally quite positive views on containers. They're very good for kind of sharing reproducible workflows, especially when you're kind of publishing your software. But there's lots of issues with it as well. Containers are just kind of basically like their own little distributions, and people have less impetus to kind of update the software, and then how long does it take to do we kind of keep supporting all containers?
Yeah, how can you, if somebody's got their own kind of little world in a container, how can you encourage them to keep up to date, essentially? Because there is that pressure, isn't there, in the same way?
And just like extra floats of having multiple containers, instead of just having a central stream of like modules. And there's like discussion on how you would kind of manage like a repository of containers, and kind of like what's the workflow as well of like you sometimes you don't just want to use one container, you want to kind of mush containers together. What's the workflow for that?
Yes, combining containers.
And yeah, apparently CERN has been doing this for a long time. They've got like a whole cluster that just uses entirely containers. So maybe we should go to them.
I think on our cluster we did a similar thing. We didn't tell the users. Well, we did tell them, but if they requested vanilla, what they actually got was a vanilla container, because it meant we contained them nicely. And it made upgrades a lot easier because you could upgrade stuff in the background, and then their containers were all static. Dean, I think you were on ownership and responsibility.
Yes, so ownership, skills and responsibility. So we actually did end up talking about containers versus native HPC quite a bit, because we got into that whole tug of war between Doug and Hunchcock, between kind of users and the admin team, and whose responsibility it is to maintain software and fix software when it no longer works. So we got talking about lots of the different methods there are out there, different sort of software distribution methods, such as the EC repo, ESSI. That has like it still uses Zen modules, but it's almost like a ready to go library of Zen modules that anyone can use on their cluster. It has an abstraction layer. We talked about ways in which we could perhaps clarify better where the lines in the sand are drawn in terms of responsibility. So perhaps institutions need to think about being a bit more detailed in terms of service with their users, about where the responsibility begins and ends for the software environment, and perhaps considering things like full RACI matrix that people can publish to their users to kind of set expectations there. We did talk about containerization quite a bit, and moving between clusters at different institutions, and how I guess a standard needs to kind of emerge to help people move more portably between them.
That leads us very nicely on to the next topic. Yeah, we're running a little bit over, so if you wouldn't mind. So and then I think I asked Marion if she wouldn't mind feeding back for the end table.
Need to support users are quite heavy on their own machine and their local data, and they will optimize for that, and they know the local stuff and talk to them, and it's all fine. and only if they want to forward, that's actually necessary to think about what do I need. But then on the other hand, people do have these make files with a statement or with a specific CMake and all. And so, and of course, Google's keynote on Monday or just writes it. Then we had a couple of horror stories about absolutely not standardized stuff on supercomputers, and also even how to get the information that is standardized, and you kind of need to find that original email where you were told where to find.
Yeah.
And how to,
Yeah, if you can't find I'm going to repeat that one because I don't think the online people can say, if you can't find the original email when you join an HPC cluster, how on earth are you going to know whether it's in the man, the info, the web page, whatever? You just need that piece that you got when you started. Sorry.
not everybody loves containers. That's a good way. Some of and yeah.
Yeah.
There's one point I think was raised something like it was like maybe we idea to have standardized environment variables, even like put points into where your temporary storage is, or your like this kind of like kind of the software packages and modules, like where their kind of their root directory is. And how you're gonna,
Yeah. Yeah, the standardized environment variables, and it ties in with that CMake concept of kind of CMake goes and gets those standardized and creates those standardized environment variables in areas. And so that whole process of moving from one place to another and knowing that when you get there, there'll be something called, I don't know, scratch area or something that you can pull and use in your code would be quite useful. So, Anna, let's see if we can bring you in. Can you unmute? And...
Hello. Is that working okay?
Yeah, loud and clear.
Perfect. So there were just 3 of us online. We started off with a chat around containers, particularly focusing on sort of the role they can play in reproducibility, and then sort of went off on a bit of a security tangent. And then one of the big questions I think we couldn't answer but were very keen on was the one around balancing reproducibility against performance and maintainability, and that was definitely one the group was keen to hear other people's experiences of, anyone who's sort of successful in that area to get some ideas from. And then just moving across to ownership, we had a chat about sort of working between infrastructure engineers and RSEs and how that balance can be achieved. But we focus more around the skills gaps, and one of the big ones there was around AI and how can you support new users coming through who are doing things that we don't understand yet, but also not being able to find the time to actually learn about it. And that was a big gap, but also sort of are not able to actually fill that gap just because of other requirements and sort of firefighting that's going on within the teams.
Yes, there was a comment on the end table, I think, about needing more support because the users are less technical, and that makes a big strain on teams that are used to supporting people who go away and read the documentation and understand how it all works, and that's not your average kind of user anymore. And I think the end table had some discussions about containerization versus kind of performance, and there was a bit of discussion about how deadline pressures change the drive for performance in optimization. Sometimes as you're nearing deadlines, you just want it to run, and maybe you're not so worried about how quickly it runs, and then the optimization happens later. And then, as I say, that trade-off being a case of, well, is it worth me spending 2 days of optimization time on the performance if I'm only going to be running a small amount kind of later on the compute, and the cost of people's time versus the cost of compute time, which we weigh differently if you're the person building the compute versus the person building the software, because the compute person will say, well, the computer's very expensive, but the software person says, well, my time is very valuable. So yeah, and I'm not sure, and it would be interesting to know whether there is any actual documentation about the performance hit of using Docker versus on or Aptainers or containers of any sort versus the their infrastructure. I'm guessing Sylvia, you must.
We did at UCL's on Zenodo some performance testing, mainly for NVLinks.
Mhm.
And we did on the bare metal GPU node. Then we did it on Kubernetes, and we didn't see any differences. Well, I mean, the standard deviation, there is no.
And you said that's on Zenodo.
Since Zenodo, I can ask for the correct link and I can send it to you.
That would be fantastic. So apparently UCL have done some tests, and just repeating so it gets through to the mic because I know these don't pick up the back of the room quite so well. UCL have done some tests where they were looking at bare metal with NVLink versus Kubernetes, and they're saying that it's within the margins of error, the difference between using a containerized session. There's another
and everywhere we're deploying it, differences are 1 to 2%. So nothing.
So that was a Net Plus group, and they're saying differences of about 1 to 2% is all they've seen. Another one.
A lot of historical publications from NERSC, DOE facility in the US, and they also focused on the file system aspect, and they're able to show the, especially for like loading PyTorch, so Python environments, they're able to show massive speed ups at scale for using containers. And there's I can't remember the name. There's a Livermore benchmark, which basically creates a fake Python environment, and you can tune in like how massive you want that to be, and then you can use that to benchmark your container and your file systems and so on.
And that's a Livermore benchmarking.
I think it's called Dynamic.
That sounds like that.
It's a really old benchmark because they were futzing around with some weird kernel modules. This was pre-containers, but it's been adopted in container like middleware testing processes.
Do we know? I'm digging. No, we're going to coffee break. We'll have to wait. So that sounds like they were doing some tests on the storage, and they were actually finding improvements by using containers for loading Python.
Mostly, especially in Singularity, where you have a single CIF file.
Yeah.
Python. Don't get me started about Python.
We're about to get a Tina rant, so
it does so much small file IO. I mean, not even in a sensible way, sort of like.
Can we take this to coffee, Tina? Because we're 15 minutes over already. Thank you very much, everybody.
Okay. Right. Welcome everyone. Thanks for coming over in the rain. My name's Dean Rowe. I'm co-investigator for the Asset Hub, and I'm here today to talk to you about a hackathon that we run, and hopefully encourage you to get involved in the next one that we run. In my day job, I'm the head of research computing at the University of Surrey. Work? Yeah. Okay. So Helen dragged me all the way up to Durham and then stole my first slide on the train on the way up here. So some of you will have already seen this because she went and used it before me as well. But just to sum up, we're a DRI training hub funded by UKRI. We are sort of aimed at training and upskilling research infrastructure engineers and supporting research infrastructure engineers, particularly kind of with a focus on early career ones as well. And we aim to deliver industry trusted training and hopefully, build teams and build stronger teams to answer to the rising AI demands in the UK and globally. And we're made up of people from Surrey, Oxford, Bristol, Imperial, and Sheffield. Okay, so the hackathon. We ran one. We ran one on the 21st of April. We hosted it at the University of Surrey. We had people come from all over. People came from 16 different universities and institutes, and we had around 25 engineers in attendance. Research infrastructure engineers. We had some RSEs. We had some end users. It was a really good mix of people. And the aim of the hackathon really was to get some hands-on time with a monitoring stack, particularly Grafana, Steams, Prometheus, and build some dashboards from scratch. So other than the fact that we had some co-design days, and there was lots of chatter at the co-design days about wanting to get hands-on with performance monitoring, why did we choose it? First of all, as your GPUs are the most expensive resource in the cluster, so if we can better monitor them and even achieve like a modest uplift in their utilization, then I mean it pays back the engineering time that it takes to build a dashboard, so why not? But as well as money, there's the green angle. So you know, the GPU power draw is the most dominant component of your energy bill if you're running a GPU cluster. So the green impact of being able to monitor your utilization and make sure you're efficient was also another reason. Evidence-based operations. So yeah, if you're able to, at a glance, look at a dashboard and get insight into user-based tickets and requests for things like this cluster feels slow, and you're able to kind of turn those troubleshooting exercises around and give answers based on hard data. And lastly, because dashboards are a really good way of giving your end users actually direct access to look at that data for themselves and just cut out the middleman altogether. So the format of the day was essentially kick off and introductions. Lots of people turned up to Surrey, we welcomed them, split them into groups of 4 or 5 sort of RSEs. We had a brainstorming session where each group came up with some ideas for potential dashboards. We then spent the day sort of 4 or 5 hours really of uninterrupted time just prototyping, working on the data, building dashboards. And then at the end of the day, everybody came together to show what they built, talk about what they've learned, talk about the challenges that they faced. These were the tools that we explored on the day. So SEAMS is, I think that stands for Compute Energy and Efficiency Monitoring Stack. It's a Prometheus exporter, and essentially its main focus is around per job energy usage and per job efficiency, and kind of feeding those stats back to Prometheus. Prometheus, some of you probably already use it. It's very popular sort of monitoring tool. I think it spun up out of SoundCloud originally, but has been widely adopted. It essentially collects metrics from an endpoint and exposes them on a HTTP endpoint, which it then scrapes and stores in a time series database. So it's we exported the data from SEAMS, Prometheus collects it, stores it, and then the third part of the puzzle is Grafana, which you use to actually build your visualizations. And that was really the main bit we were working on the day, was building the visualization, but you need to understand kind of how the data moves through to get there. Just a couple of examples of what was actually built on the day. There were 6 or 7 groups, so I've just got 2 examples because these ones were the prettiest. So the first one is team number 2 on the day, and their dashboard was, these people had never built a Grafana dashboard. Actually, team 2, they'd never built. They'd never worked with Grafana. There wasn't anyone in the team that had. So they just went for a general kind of cluster overall utilization dashboard. And I think the target audience for this was kind of admins and PIs. Team 3, which was the team that I was on, was more around building a dashboard for management to understand which GPUs in the cluster were the most utilized GPUs, what was the average utilization over time periods, which you can adjust and see. And I think the idea in this was to help kind of management understand where should they invest, which are the popular GPU types, where should I be investing my next procurement exercise in, which GPUs can potentially I drop off the cluster if they're nearing end of life. So there were many more examples, but as I say, those 2 look good on the slide. So I think there were some things that worked really well about the day. I think tailoring the dashboards to different audiences worked well because we ended up with a diverse range of dashboards. We did use real like live data from clusters, one from some data from some Surrey clusters, but we also had other people bring clusters with that, kind of bring a cluster with them. So that doesn't sound possible, but brought remote access to a cluster. So we had some live data from other clusters as well. That was really good, and obviously meant that some people built dashboards they could then take back and use straight away. Small teams, 4 or 5 people worked really well. It was just the right number, not too many. Nobody was sort of carried. It wasn't small enough that you could hide, but it was also big enough that you had lots of different people contributing. The one-day time box format worked really well, kept things focused, and the breakout booths, the venue worked well because of the breakout booths. Some lessons learned for when we do the next one. There was obviously some issues on the day with kind of getting accounts, getting people connected to Wi-Fi on their personal devices. I think we learned some lessons there around prepping ahead of time for those, prepping better ahead of time. We did prep, but prep better. There was a kind of bottleneck around that initial brainstorming session where sometimes you know what it's like writer's block where you've just got a blank piece of paper. So I think pre-prepping people with some ideas before is probably a good way to kind of condense that part of the day. And the 2 major lessons, I would say, the 2 major takeaways for running a day like this was it would have been really good if people had familiarized themselves with the data format and the kind of schema in which Seams exports its data, because there was a lot of time spent on the day, probably the first 60 to 70% of the day was people just wrapping their head around how the Seams data looks when it's exported before you could then turn that into something really useful in a visualization. So it's as horrible as the word homework sounds, actually some homework before the session, I think, is something that we could perhaps think about for when we run another one, so that people can really hit the ground running on the day. And the last thing was we had some subject matter experts, but we embedded them in the groups, in the teams, and they would end up getting kind of dragged out of those teams to help other teams, thereby abandoning their teams because they were spending a lot of time helping other people. So I think something we've learned there is to have just kind of floating experts next time. We got some really good feedback after the day, and the main one I want to draw your attention to is a little graph down the bottom, which is basically just people's own feeling about how confident they were before and after. And I think that's a really encouraging shift into some people feeling very confident about their abilities in the topics that we covered, and no, not at all confidence at the end of the day. So that's really good. That's what we want from a day. And if that sounded at all interesting to you, please join us for the next one. There's a few different events which Helen already mentioned this morning, but the one I guess that I would like you to all think about is not up here.
The middle one.
Oh no, yes it is. Which one is it?
Middle one, 15th.
This one. Oh yeah, the 15th of September we're going to run a Slinky one.
Yes.
So yeah, if that sounded interesting to you and you think Slinky is interesting, then we're going to run a similar kind of hands-on session. It's going to be distributed in 2 different sites. So one, if you're nearer Sheffield, go to Sheffield. If you're nearer Surrey, come and see us. Weather might be better in Surrey. But yeah, if Slinky is a bit of interest to you and you want some dedicated sort of hands-on time to just play around with something new, which let's face it is quite hard to come by in our jobs, then yeah, please come and join us.
Can I ask what is Slinky?
Slinky, good question. That's what I want to learn that too. So I'm going to go to the hackathon. No, I think it acts as a bridge between Kubernetes and Slurm.
Okay.
But it also works the other way round as well. I don't know, so I'm going to go to the hackathon and hopefully find out. But yeah, we are also, I think, Helen, we are looking for experts, aren't we? So if anyone is using Slinky in production and actually wants to come along to the hackathon as well, we are looking for kind of those subject matter experts to help us out with that. So if anyone knows anyone, send them to Helen, and she'd really appreciate that.
Let's at this point take someone that runs Slinky for testing. I haven't actually found anyone that tested out yet.
No, this is the problem.
Well, the Stack HPC guys.
So the Stack HPC that I have, and there was somebody I was talking to earlier who has who's tried it and is now not using it because they moved institutions, but they were trying it before. So there are people out there, and we have got some of them on board. So we're not completely looking for experts, but any extras would be welcome to come and join in.
And yeah, the idea is I think on the day there'll be sort of a cloud provision sandbox for people to kind of play around in and get some hands-on time with that. So yeah, I think that's it. QR codes there if anyone wants mailing lists or anything. That's it. Yeah. Thank you.
I was going to say, you could probably see that the event before the hackathon was the hackathon prep webinar, because we learned from last time, and this time we're going to try and prep people.
Yes. Yeah.
Introduce Tina, or shall I?
You can if you want. If you want to stand up for me.
I will. Let me just log into my laptop so I can give my laptop sort of like consent to let me do that, so I can start sharing slides. I tried to get me back to the meeting. I should be in the meeting.
It did this to me earlier. Logged me out when I stopped sharing slides.
No, it's doing the I haven't got a network signal thing, which really should be a problem because there's a lot of anyone.
So there. Dina has very kindly, with the help of ChatGPT, I do believe, written some images.
Yeah, but I haven't actually written, and I took most of the images out. So
Did you?
Yes.
Oh, okay.
It's sort of like, I mean, there's only one or two of them left. Or sort of, I did like them.
I think they're brilliant. I want them for the website. There are some lovely explanations of how to schedule as well. So, so to those of you who are already heavy HPC users, and I'm talking really heavy HPC users, you might feel a little bit like some of what we're about to discuss is teaching you to suck eggs, but this is about preparation for discussions that are coming up around HPC schedulers and what works and what doesn't, and how we might want to look in the future. For those of you who've never touched an HPC scheduler before, this might seem like it's all absolute magic, and you had no idea that schedulers could do some of these things. So it's we were aware that there's a huge range of kind of abilities that in this room, and then I set Tina the task of trying to demystify the scheduler for that wide range of abilities. So hopefully she's got enough to start some discussion. Are you right, Tina? Are you?
I'm still working on the actually getting it sort of like to log me into Teams again.
Fun.
I did tell you that you can't trust it.
I know we have had this discussion a few times.
Right.
There we are. You're in.
I am sort of like. Let's hope they're the correct ones. If they're not, I might have to go through this again. Right. I have notes as well, but I'm sure I probably not need them. As Helen said, she set me the task to sort of like sort of write us up on demystifying the scheduler. Sort of like thinking about this. Hang on. There's my window. Hello? Yeah. After some thinking about this sort of like, I came to the conclusion that really all I could sort of like do was sort of one of them, so I picked Slurm. I mean, I could have done a real thing and sort of like picked any of the others and you'd look at me even more baffled. And then Helen sort of like told me that you definitely all know what a scheduler is and things like that, so I should make it advanced users. And yes, as she said, sort of like I did ask ChatGPT for the graphics, which is not a thing I normally do. Anyway, I'm not sort of like, I have way too many slides, I'm just going to run through it. Right. Just as a recap, sort of like, because I find it helps to do these things. What is a scheduler? What do we mean by the scheduler? Because the thing is, sort of like, there is no such thing as the scheduler, sort of like. There's tons and tons of applications that do this sort of thing. In this HPC context, what we mostly talk about, is Slurm, but what we mostly talk about is any of the various applications that you can use to sort of like hand workload to, and they're going to figure out how to sort of like put it to something that can run this workload. Slurm is by far not the only one out there. It is a very widely used one. That might change depending on NVIDIA are going to do with it. It didn't used to be the one that most people used, sort of like when I was starting out, and this grid engine was much more common, and then Oracle happened.
History repeats.
Things like that. So, but basically, it is an application that facilitates the unattended execution of workload on something. is what we normally refer to when we think about that. And the problem we're trying to address is the basic problem of there being more work than resource. And all the work needs different type of resource. And how do we maximize the utilization of that resource, juggling all the other bits that go along with it, like sort of like everybody wants to use the resource and it needs to be distributed to all people that want to use it sort of like fairly. And people shouldn't have to wait too long and all of those things. Anyway. Why is this a problem in the first place? Because, I mean, surely the solution to it would just be to have enough resource for everyone to just use it at any time, which is sort of basically the idea behind AWS, which is why they've very nearly reached the stage of the small star or something like that. It's fundamentally, there will always be more work than resource, at least in our space. And yeah, we can throw money at the problem, but somehow there isn't an infinite money tree. Therefore, we have a problem.
And even if there were, there would be infinite power.
There's that as well, sort of like the infinite money also doesn't sort of like, I mean, we cannot, there's a limited amount of power we can actually produce. Or computers that we can actually build with the things that we dig out of the earth to do so and things like that. So, yeah.
And then people would also complain that there would be machines that were idle.
And then when people would complain, that's a really good point, sort of like we'll have that discussion later. Anyway. No, this is the next slide. So the theory is sort of like that we take all the work that we have and we make the best efforts that we can to fit it to the resource that we have. And the best efforts, and the scheduler's job in this really is sort of, so this first point there, it allows you to queue jobs. Now, I know that to most of you, that doesn't really seem like a blessing, but boy, is it. Because otherwise you'd be sitting there waiting for a slot to become available so you can grab it. And then all these other things that I've already mentioned. It generally, that's part of the thing, sort of like, at least classically in HPC, the driver for the resources to be as utilized as possible is important. Anyway, yeah. In practice, one of these things does normally sort of like not quite fit, and normally it is the workload. So in practice, you generally end up with something that is trying to make the best to sort of like go through a queue of workload that is way longer than all the things that it has. And so a lot of it also then comes down to how do I organize this so it does feel fair to everyone and everything comes down to you can use the thing. And especially in Slurm, which is why we're coming to this now. One of the main things that it sort of like uses is how it prioritizes work. And this is also the thing that sort of like trips most people up because they don't understand it. I'm going to try and give in the next couple of slides, give an overview of how Slurm prioritizes work to let you into a secret. The people that run Slurm clusters also don't understand how it does it. So the theory behind it is very nicely described for the most part in the documentation. There's some factors in there that the documentation actually doesn't mention other than they exist. So you have to actually go to the source code to try and find out what they actually do, which I gave up on once I tried. So this isn't sort of like, yes, okay. This is sort of like, the thing here is that best way possible and fair, especially in Slurm land, it's a very configurable sort of thing. And that's an annoying thing about it. But it's also a really powerful thing about it. And it's actually one of the things that is, because it's not the best thing at the scheduling of the workload and things like that. There have been other schedulers that I've worked with that are much better, but Slurm's really good at the prioritization and policy settings. In a way that lots of other schedulers aren't. But that also is why it can be so hard to understand. So fundamentally, Slurm itself, and up until very recently that would have been the default, doesn't actually prioritize anything. The basic scheduler is a FIFO system. It does job in, job out. There's plugins that you can use and utilize to do the prioritization. Basic is the FIFO thing. Priority multi-factor is the thing that is normally the default these days and that most people run, sort of like. You probably wouldn't do the basic unless you actually schedule it externally, which is the thing that you could do, but I don't know anyone that does it. The priority multi-factor plugin. And this is sort of like also that there's going to get, because people always sort of like lump that in with fair share, which is sort of like a factor in those, but they're not the same thing. The multi-factor priority plugin is not sort of like actually sort of itself handling the fair share allocations. The fair share is one of the factors in the multi-factor priority plugin. So the order that jobs are prioritized in is that. And job priority, which is where the fair share comes in, is actually fairly far down the stack. There's a lot of things that it considers before that. A lot of these don't always apply. In fact, a lot of these quite often don't apply. So you kind of end up with the fact that job priority is the thing that it mostly is about. But I run one cluster that has a petition priority. So and advanced reservations is a thing that happens quite a lot and things like that. But in Slurm's view of the word, these are actually just factors in its prioritization logic, not factors outside of it. And yeah, the takeaway thing from this is sort of like the job with the highest job priority in a scheduler's mind might not actually be the thing that it considers for execution, even if that looks slightly strange to everybody using it. Right. These are the factors, according to the documentation. I did not go into the source code to verify it, that it considers. And that's and the association factor is the one that nobody seems to actually know what it is. I think it's just an arbitrary number that you can actually. Do people know what an association is in Slurm? An association is the object that comes out of taking a group and a user. Sort of like, and maybe a quality of service and a petition that they're allowed to access and things like that. So in Slurm, you define projects or groups or users or accounts or whatever it calls them. Accounts, I think, accounts. So you define accounts and you define users and you put users into accounts, and also things like you have access to this quality of service and these resources and blah, 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 and these are your default settings. And the thing that sort of like says, this is the account, these are the users, these are the default settings and things like that, that's an association. And I think what it boils down to is you can simply assign a number factor to this association to give it a priority impact. There's a fair share. We come to that sort of like, and at the end of the day, you've got factors for all of these. Some of these are hard set, some of these are calculated. They depend on lots and lots and lots of things, and then it takes a weighted sum. And that's your job priority, and that's the priority that's assigned to the job. What the ratings for this are is down to local configuration. So the fair share factor is one of these, and the fair share algorithm is actually sort of like, it's a tree algorithm. It's actually quite simple. Sort of like if a project has a priority, the children of that priority sort of like inherit that. So you don't have higher priority children in lower priority projects and things like that. So it's an inherited sort of like thing. And and then you assign shares to the associations in your fair tree. And the shares basically say this much of the, and they're between 0 and 1, but it's really just 0 and 100% and things like that. Just normalize. Slurm normalizes everything down for reasons. And basically, 1 just means you should be getting the whole cluster. And 0 just means you shouldn't get any bit of the cluster. And you give everyone a share that they're supposed to be using at the cluster time. And Slurm's really happy if their usage match that share, because that's what it's aiming to do. A fairly common setup for this is everybody gets the whole cluster. At which point, Slurm is going to try its damn hardest to make sure that everybody gets the same share of the time that it can allocate. But there might definitely be setups where, for example, 2 groups bought a cluster together and one bought 80% of the nodes and one bought 20% of the nodes, in which case you would set this differently. Right. just to have a really quick, really made up calculation. Suppose you only had these 5 factors configured, and that you can just deactivate any of the factors in the configuration by simply not giving them a weighting. So they're all really tunable. Suppose we had these sets, that's what the calculation would be. And if we then had these 2 jobs that come along with those factors, that's the priorities that come out of it. Nice thing about this example is sort of like, in this example, job B is actually older. It's been in the queue for longer. But because of job A's much higher fair share value, it would still be scheduled preferentially. It would win the battle of whose workload is more important, sort of like. Even though it's not really about importance, it's yeah. Anyway, the reason it normalizes everything down is because it also has a notion, and it leads to set so in the documentation, that no 2 jobs shall have the same priority. And it ensures that by sort of like normalizing them all down and then rounding them so that the rounding errors take care of it, which is such a slow way to do things.
Written by an engineer, not a scientist.
Yes. Right. We now leave priority and fair share behind. That was a very quick overview, but I hope it clarified things a little bit for people. Scheduling, that's another of those things, sort of like, not a lot of people are aware of this, but Sloan has 3 distinct scheduling loops. It does not do one attempt to schedule a job. There's multiple bits that work at this. There's an event-driven thing that's sort of like, and I'm not going to what the depths and things are. When a thing happens, like a job starts, a job stops, or there's a reconfiguration, I think that's the 3 triggers for this. It does a direct scheduling attempt. And that's a really quick and dirty one. It's the lowest queue depth and things like queue depth, and this is sort of like the depth of the stack that it considers for execution before it gives up. A really low depth for that. But basically, whenever you submit a job, it would immediately try to see if it can quickly execute this. And some other things and things like that. So every submission of a job, every exiting of a job and reconfiguration events will all trigger a quick scheduling loop to see if there's anything it can do. There's the main scheduling loop, which runs periodically and basically considers all jobs. For various definitions of all jobs, there's all things in Slurm, but it mostly considers all jobs and evaluates jobs in strict priority order. And then it places them sort of like onto the cluster, especially the big ones. And it will do, Slurm does some really complicated, Slurm, it has a fairly complex scheduling algorithm, and it tries to basically do some sort of mapping and future predictions of how the resources will map the workload. So it doesn't simply just do a, can I do this job, can I do this job, can I do this job? It sort of like tries to do a projection of what its resource space looks like and what its job space looks like and how these things might best fit together. And this main scheduling basically sets the cornerstones of what it knows the job executions are going to be. If in lots of ways, think about it as sort of like it puts the big jobs and the things that it knows it has the resources for at those times into place, and then they sit there. And then there's backfill, which sounds like just a little thing, but it's actually the most complex, complicated, and most, that's the thing that runs most jobs. What the backfill scheduler does, it also runs periodically, but much more often than the main scheduling loop. And it attempts to fill the gaps that the scheduling algorithm of the main scheduler loop leaves. So basically, the main scheduler says, these are the things that I will execute. And the backfill scheduler will never mess with those things. The backfill will not change the scheduling of the jobs that it has the resources predicted and in its own mind allocated to. But it then goes and looks at the jobs it's got in the queue and sees if there are any that it could allocate without taking any of those projected resources away from the things it's scheduled. It will at that point very nearly completely ignore any prioritization, because at that point what it wants to do is make sure the resources are full in such a way that it will not ever impinge on its prioritized scheduling. I hope that makes sense.
That sounds like, as an analogy, in the project management office at the uni, they use this rocks, pebbles, and sand analogy.
Yeah, this is the backfill is the sand.
Yeah.
Backfill is the
And
sand.
it won't ever change the pebbles and rocks. Yeah. It's
Tetris.
It's the next piece where you can see the next.
Apart from you play Tetris with everything coming from one direction.
Yes.
You don't sort of like, this is basically when somebody's messed up their Tetris board and you then throw the blocks at it to hope that it fills the gaps.
So when I tell people request few resources in a very short time, I'm telling them that because the backfill should pick those jobs up.
Yes,
They're not going to get
that's
it from the first
precisely it. But the thing about the backfill is the backfill will not ever be the thing that disturbs your job execution time for the things that it has scheduled according to its prioritization. It does not make allowances for backfill jobs or juggle other things around. It strictly only fills the gaps that it can fill. Even though, I mean, there could definitely be scenarios where you look at it and go, like, this is 5 minutes. If you would just move this job by 5 minutes, you could do so much more work. But it's not smart enough for that yet. I mean, we might get there, but at the moment, that's what it is. Yeah. On any of these calculations, Sloan can only do this if it actually knows what the jobs want, how long they're going to run for, how long they're going to sit in the queue, what their footprint is, all of those things. The time is actually, in lots of these things, the time of execution is a really important one, because if you just sort of like run with the petition limit and things like that, and that's like 12 hours, but you know your job's only going to run for 5. Well, if the scheduler thinks the job's going to run for 12 hours, it's not going to try and fit it into a 5-hour gap.
So if someone's got, I've got an 8-hour job and it fails after 1 minute from some small error, will the backfill still then be able to...
It will at that point be gone from the queue, and the next time the loop runs, it will reevaluate the spaces and things like that. But it's sort of, so if something fails quickly, that's much less of an impact, because these things run often enough to sort of pick that up. It is really more sort of if someone's given a totally wrong prediction.
If you put in 8 hours and you run for 5, then it may have at hour 4 have put in a 4-hour job, and then it can't take that 4-hour job off just because you finished 3 hours early.
Yes. So it's not only about it can't fill your job in. It also means if it's waiting for this job that you told it is going to take 8 hours to free the GPUs on this node so it can schedule the thing that it's scheduled, it's put that into the scheduler in 8 hours time and booked the resources for it. If the resources suddenly become available after 5 hours, it could have started this job earlier, and his view of the work would have been very different. It cannot make those predictions without knowing to a fairly good extent, or rather, it's much better at making those predictions well if it knows what your resource requests are.
This is actually one of those, I think, evergreen contention points with what I would call non-traditional HPC users.
Yes, because they don't understand why it's so important.
It's not just that.
They don't know.
Sometimes there are science problems where you do not know, like it could be like an inverse problem that's iterative.
Yeah.
And it's based on measurement data.
Yeah.
And you do not know, does it take 1 million iterations or 10 iterations?
But mostly you can check both those.
Yeah, try to make, okay, that's it.
There are discussions afterwards. We will get into all of this.
Anyway. And with all that knowledge, you still look at the queue and there are nodes that appear to be idle. A lot of the times that is down to, it's sort of, so the thing is, if Slurm thinks it can't schedule for something, there's probably a reason for it. It's not very forthcoming with what that reason might be, regardless of how well you try, but there is probably a reason for it. And the thing, Slurm does not only take into account things like the CPU cost, the RAMs, the GPUs, or the resources you have. There's all these other things. NUMA localities, what the reservations are, the network topology, storage space, depending on how your cluster is set up, all these sorts of things. And some of these things is also really expandable, right? I mean, I seriously, honestly, I did not give it many briefs for that, and It came up with that on its own.
Okay.
I can't remember those.
It has to optimize all the things.
All your bases are being
But basically, yes, it's sort of like the picture you have, looking at this and thinking, but there's idle resources that could run my job. That might not be what it's seeing. And there's probably a reason that thinks they're not idle resources that could run your job. What these are, yeah. The CPU binding or rest binding, because I think I mentioned it later, but it's sort of like the binding is actually one of those things that it is that can mess you up there quite often, because by default it will. By default it will socket bind. But to the local Slurm will not schedule you to a GPU if it cannot schedule through the local socket. And that's annoying, but it will not do it unless in your job submission you tell it that that's okay. But by default, it will strictly bind things, or in the configuration, I think, but I'm not actually sure if you can change that in the configuration. By default, it will strictly bind things to its local socket. And it does have your CPUs and memory and all of those things, as far as I know. It's sort of like it will sort of like heed the internal node configuration in its scheduling decisions, so you don't end up with inefficient communication path nodes internally. Binding options are enforced sort of like SRAM node partition and global configuration, sort of like. So in this, always, and it is SRAM, and it is also trips me up all the time when I want to read this up. The documentation about how to set binding options is in the SRAM men page and in the SRAM men page only. It's not mentioned in SBAC or SLOC, mostly because it's job step specific and it is SRAM that is the task launcher. SBAC and SLOC only do allocations and do not run tasks. So you can always override this with the SRAM options. And that's the level of sort of like that it goes through to look at what it should do with the bindings. Some of the options for your, and I just put these in so because people often haven't seen those sort of like, because it's got more options to sort of like tell it what to do with the CPU binding than you can shake a stick at, and probably more than are sensible. Because the most sensible thing to do is basically to leave it up to the scheduler or the kernel to sort of like, because it knows what the node is. But you can actually set the affinity mask for your CPU on job submission. Right. Generic resources, that's actually what it stands for. Generic resources, arbitrary resources. The most common of those is a GPU, but you can write your own plugins to define site-specific ones and things like that. So really nicely defined APIs, actually nicely defined, it's not even hard to code to. The GPU one is the one that sort of like most people are aware of sort of like in this. Most modern bandwidth is one that also, and Nick sort of like access is one that is also quite widely used. The important thing there is, and this trips everyone up all the time, internally to this day, this is handled on a socket basis, not on a core basis, but it is exposed through the options as if it were done on a per core basis. And most of the times that's not a problem, because if there's a core and a socket, it'll transport to a resource, but that can actually cause problems because it is internally in Slurm's internal logic always on a socket basis, not on a cores basis. Right, network topology is another one of those things. That's actually it's got really low timeouts for this. So sort of like under normal circumstances, and tree topology is the most common one that people sort of like set in this. So basically, Slurm in its configuration file sort of like has been told that these switches talk to these switches, and this is how you go up and down the tree. And when it does scheduling decisions, it will basically start at the lowest switch that it can go to and then go up the tree until it finds enough resources to schedule you to minimize the path between things. But it's got a really low timeout for this sort of like, so basically it does that in a way that sort of like basically says, yeah, I'll heed that, but only if I can start the job within 10 minutes or something like that. And otherwise it might ignore it. And switches equals 1 is the normal sort of like thing. The timeout, you can actually tell it from job submission. So if you'd really rather it's on one switch and you'd rather wait longer, tell it to wait longer. And it's configurable as well, of course, and things like that. But it's sort of like, so the network topology people quite often assume is really strict, and it actually isn't. Not in the tree setup, which is the normal sort of like one. There are other topologies that it can live with. Block would be the thing that enforces the stay within your local block, sort of like much more strictly. There's ring and torus and sort of like it knows about all sorts of network topologies. None of these at the moment are auto-detected. So they're all things that need to be set in the configuration by whoever administers the cluster. And you have to, of course, sort of like tell Slurm that it actually should look at the topology file and the scheduling decisions. This is not always sort of like a thing that you need to do. It makes most sense in sort of like low latency networking and things like that. If your cluster is mostly a throughput resource and you don't really care because you don't really do a lot of MPI workload, you might not be bothered about that at all. But it could also have things about locality of storage resources and things like that that you want to heed in its scheduling decision. So yeah. Anyway, resource limits. They're not sort of like this is literally just in there to sort of like remind people that they exist, because there's another knot that you can twiddle to make sort of like things be a bit more like you like it usually, because you can set limits on pretty much everything that can be scheduled by Slurm on a basis of partition, job, user, account, the full cluster, or not at all. It's and you get yeah. And I mean, this is, I mean, pretty much everyone has those, because pretty much every partition that I've ever come across, well, most people will probably work with partitions that have time limits. That's a resource limit. Right, quality of service. Another one of those things that admins talk a lot about, and it's a bit watery. A quality of service is basically a way to sort of like set the resource limits on a bit of a smaller scale than all of the other things, or set them a bit more flexibly and things like that. It's basically a quality of service is basically an object that sort of like defines things like it can affect scheduling, priority, preemption, and resource limits, basically. So you can give everyone sort of like the same sort of job priority, but you have a priority for really important jobs that people can sometimes request, or something like that. That just gives it a priority boost when it goes into the queue, because that's the initial scheduling priority and things like that. Preemption things, resource limits. So, for example, it's perfectly possible to have a quality of service that people have access to that allows them to ignore the time limit on a partition. I have such a thing. They're just a way to influence sort of like behavior on a slightly smaller scale, but very flexibly. You can do virtually everything with it. That's a lot more. I haven't even mentioned things like, we haven't gone into preemption or checkpointing. There's a lot of accounting that it does. The accounting is really quite excessive, and most of it you can look at yourself, at least for your own jobs. Job arrays. Heterogeneous jobs, which is one of those things that would be really good if you could do them one after the other and not always at the same time. But Slurm is perfectly possible of you submitting one job that needs 3 different types of resources for 3 different job steps, and handing them to you and things like that. Job dependencies, which is kind of a useful thing actually, and there's so many options to sort of like set job dependencies. Containers, which it has some native functionality for, and we also have the Slinky coming up and things like that, but there's a nice REST API. Does do namespaces quite nicely these days, which is actually quite good. There is actually a Slurm command for telling it to move your data somewhere, please, before your job starts. Not many people seem to know that. Prologs and epilogs and all these other things. Yeah, there's so many things. Gang scheduling, not even wanting to go there. And it actually sort of like, I always say to people, if you use a cluster a lot, it's probably worth looking at the documentation once, so you actually have a bit of an understanding of the information flow and the purpose of things like SLOC, S1 and SBatch actually is, because they're not exchangeable. They have very different sort of like purposes in the lifetime of a job, and it's actually, it helps if you understand what those are. It's probably SLOC and SBatch do the same thing, in which they create an allocation. SLOC is interactive and SBatch is a batch allocation. SRun is the only one of these that can actually launch tasks, and it launches tasks using any subset of the resources that the allocation requested for you. So technically, you sort of use that to run your parallel job steps. The only reason that you can use MPI run for this is MPI is normally built against Slurm and uses SRun internally to do so. So you don't have to do it manually and things like that. It's perfectly possible to run other things within your job environment via SRun, using any slice of the resources it's given to you, which and gives you a nice list of environment variables to tell you which ones you have. Yeah, and as I said, we also didn't cover anything other than Slurm. Right. I'm not quite sure this is a sort of like thing. What it isn't is magic.
This one needed a cartoon, surely.
Yes, I mean, sort of cartoon one thing, sort of like, yes, but we should make one for this. And this first point, it's a bit of a sort of like sleight of hand, but if I could get sort of like £1 for every time somebody seems to think that if they just come with their single thread Python code and run it on 10 nodes of my cluster, it will magically move faster. Because they've submitted it to the HPC and surely that's its purpose. No, it doesn't work like that. It doesn't do magic with your code. What it does is make sure your code gets the resources you tell it needs. It cannot magically make your code into something that it isn't. Your code needs to be able to do these things. If your code is not written against MPI or any of the other things, no amount of requesting multiple nodes is going to make it run across them. If it doesn't thread, it's not going to thread, regardless of how many threads you give it. It's also not biased. It's not out to get you. And it isn't sentient. It can't guess what you want. At this point in time, it can't guess what you want. It needs to be told. It's actually fairly stupid. And this is a thing that Helen brought up. It doesn't have any inbuilt options for data-aware scheduling or workflows or any of those things, sort of like that some other schedulers have in quite nice fashion. Slurm doesn't. It's fairly basic in those sort of things. It's a very complex piece of software. It's trying to do things very, very cleverly. I'm not totally convinced that is always the best idea. But there we go. Right. I left this one in because I thought it would be a nice discussion point, sort of like. So, HPC admins do not as such hate interactive work. They're simply of the opinion that such things are really good for debugging and prototyping and things like that. But it's really, really hard to make interactive work utilize all resources because humans don't work like that. Humans have thinking stops, and humans work during work hours, although in academia that can sort of like be a very broad spectrum of what that is and things like that. But you sit there with an interactive session and you do some coding, it doesn't quite do what you want, and then you sort of like go away and find out why it doesn't do what you want and things like that. And all the time this resource that you've booked, that yes you want to use, cannot be used by someone else. And it's normally not easy to sort of like timeshare and time slices. There are projects that try to do that thing. There's a fundamental problem of you don't actually know when you come back and want it again. Just apart from all the fundamental problems of how NVIDIA's architecture doesn't actually allow you to do this sort of thing really well with GPUs. But if I don't know when you're going to be done with your reading of Stack Exchange or whatever it is you're trying to find the solution to your problem for, I don't know how long I can give this resource to someone else for. And therefore sort of like, and low utilization is basically a problem because these things, computers use a lot of power, and it doesn't really matter that much whether they run something or not, just because they're powered up. They use quite a lot of it, and they're quite expensive to buy. So having them sit there idle is a real waste of resource and a real waste on your investment and things like that. And I mean, yeah.
Sorry. I agree. I'm going to add a different, an orthogonal direction to that. And sometimes sitting idle is not a waste. So a resource being available to a target of opportunity can also be a value in its own. So I think as an HPC community, we are measuring sometimes the wrong thing. So I do want to, propagate it. Yeah.
Is now a good time for me to bring out the discussion point?
It might very be. It's my last slide anyway.
I was going to say, thank you very much.
How long did that take?
You're a little bit over, but I'm not complaining. I thoroughly enjoyed that. One of my old academics used to say, the scheduler isn't magic, for that we need you. And I think that's very true. So, yes, so those of you that are in this morning's session are going to recognise this slide a little bit as I pop it up. I don't know if I can.
Let me try and get rid of this so I can stop sharing. Oh, I am stopping sharing. Good, brilliant.
It's taken me right from the beginning. Right, I'll scroll straight through to this one. Yay! So, same principle as this morning. There are some, you may turn over your papers again. There are some discussion topics on the tables. We only have 4 tables though, so I've kind of moved what should come next into a generic. You can put those on any table, anything that comes up, kind of where you find issues with this and go, well, actually, wouldn't it be amazing if in the future schedulers could do X, Y, Z? And yes, infinite resources would be lovely, but that's not an effective solution. So let's look at what they can do. For those that weren't here this morning, the rule of 2 feet, optimise your time, however we want to put it. Don't hang about at a table. If you've got nothing left to say and there's nothing more that you're gaining from the conversation, please do move on. No hard feelings. You don't need to apologise, don't need to interrupt the conversation that's going, just get up and move on to the next table. And cross-pollinate. If you found something really good on a table that you want to take back to somewhere else, you had another discussion, you can go back between the two. That's fine. You can go back to where you came from. So there's post-it notes and pens on the tables. There's something to stick them all on, and if you want to kind of link post-it notes together and just generally kind of get enthusiastic and creative, you can do. I'm going to try and work out. I think we've got an Asset Hub member that I can put on each table just about. Tom, are you able to take that back table for me? Yep. Yeah. I've just had a quick chat to my facilitator in the online sphere.
Is she on her own? Is she on her own?
Not quite. There's somebody on a train. And I think we may have. No, that is it. There's just somebody on a train. So I think we're going to leave it at that point. And we won't make the online people sit and try and discuss with poor reception. So that's not fair. But yeah, so we will feedback. Where are we now? In about half an hour. Just 1 or 2 ideas from each of the tables. So let's get going.
Something like that.
So
there's web pages.
Where should we start? Should we start with one? Tina, do you want to give a couple of points that came out of your discussions about fairness?
It's sort of, we weren't actually very, it didn't seem to be a very controversial sort of like discussion. There was a lot of sort of like mention that what it definitely should do is ensure that everybody does get resources. And at some point that's definitely, it would be unfair if a job never gets scheduled.
Yeah.
And it's a lot about sort of like rewarding good behavior and stopping people monopolizing resources, because that's not a fair thing if you allow people to monopolize the resource somewhere. That mentioned a couple of times.
It's definition of efficiency.
The definition of efficiency was sort of like, because they came off of the carbon of their scheduling and things like that, because efficiency isn't necessarily sort of like, how do you define it in your local context and things like that, and what is it you're actually trying to make it do? I think that's basically it.
2, which would be Dean's table.
Okay, yeah, so ours was user input, automation and trust. We talked quite a bit about the user challenge of obviously how you estimate what runtime, what's the runtime of your job, but also what resources do you need, how do you right size the sort of resources that you're requesting. There wasn't really any obvious answers to that for that challenge. Obviously, there's a bit more around right siding your job, because you can sort of run test jobs and benchmark and change your problem size. But the runtime thing is obviously a difficult one, especially the issue that Johannes mentioned earlier around effectively not knowing whether it's 10 iterations or 1,000 iterations and in certain types of jobs. We looked at how schedulers might be able to use historical data to reduce the reliance on the user. Again, another really difficult one, and we're not really quite sure any schedulers are yet intelligent enough to be able to really do that in any meaningful way. At the end there, we've actually talked a little bit about, well, actually, does the user really need to know? Should we be striving for a HPC system where the user's understanding of the system is really irrelevant? The system just needs to understand itself, and it should all be obfuscated from the user and easy for them to use, because at the end of the day, all they care about is doing their science.
Wouldn't that be lovely?
Yeah, so I guess that's the ultimate end game, isn't it? Is to get to the point where the system sort of is intelligent enough to know itself and be able to explain the reasons for things like why the job isn't running back to the user. And we have also established that some schedulers out there do that already better than others. Condor, for it was the example that we were using, is already quite good at telling you why your job doesn't run, whereas Slam's not as good at that.
Grid Engine was also quite good at telling you why your job can't be scheduled and things like that. I think Slurm is a bit of an outstander actually in not being able to do that. Most of the others don't ever.
Maybe that's somewhere they should focus some engineering.
It's been mentioned to them before, yes.
I would like to add something else about the user perspective, is that at the end, if I feel that the maximum use time is 12 hours and my job will be in the queue the same time, if I put 12 hours than if I put 1 hour, I will always put 12 hours because it's safer for me. And I think that's what I used to do. I don't know if that is what a lot of users do. And I don't know if there is any way to show them data that say, no, they will run faster if you put 1 hour.
That's sort of like wait time versus job size or requested wall time is a fairly common metric. Yes, it's sort of like, so that can be shown.
Yes, but like from the user perspective, it didn't, like it usually is, oh, if you put it on the 4 a.m. in a weekend, your job will run like that. If you put it in the middle, so I think there's a lot of like things that affect the queues and the scheduling. So
I think this is why we wanted Tina to give that talk originally, because a lot of people don't understand things, aren't even aware of stuff like that backfill mechanism.
Yeah.
And if you're not aware of it and your users aren't aware of it, then it's very likely that they'll be doing what you're doing, and playing on the safe side and putting 12 hours because they don't understand the impact that has on the scheduler.
Yeah, and then if everybody puts 12 hours, the backfiller doesn't work because
you can't backfill anything. Yes, it's
And at this point, you need some sticks, because it's one of those examples of, if everyone drives to work, traffic sucks.
Yeah.
I'm gonna drive to work and want everyone else to take the bike.
But in order for everybody to take the bike, can we please have some better cycle infrastructure?
Yeah, so
the person who cycles to work.
Then you need good bike lanes, but also need surge charges. You need to make it actively worse for the drivers, otherwise they're never gonna shift.
But first you need to make it better for the cyclists.
Absolutely.
Because it's not fair to charge people for things and if you can't guarantee them a better service when they take the good citizenship, which we had here. Reward good citizenship. You need your carrots first.
And the the argument about should it really just be sort of like people at the end of the day people just want to do their science and why should they have to know how to use a scheduler? Well, I don't think any chemists that I know really liked learning lab rules. And yet they're fundamentally something that you have to know.
If you're going to work in a lab.
If you're going to work in a lab, you kind of have to know how to use the facility. If you're using a spectrometer or something like that, you're probably going to have to read the manual and not just sort of like expected to do things. And yes, these things can get easier, but there's a certain argument of sort of like if a tool is something that you need to use.
makes sense.
I've got some interesting thoughts on that one. And it relates to how cars have adapted over the last kind of 50 years.
Yes.
And the fact that you no longer have to heel and toe, which no one in this room is probably old enough to know about.
Oh, I do.
Hold on. Join me on that one, Tina. Heel and toe was when you didn't have a choke. Nobody even knows what a choke is anymore, because they're all automatic. But you used to, when your car engine wasn't able to cope with the fact it was cold, you could put more fuel in with what was called a choke. And you literally had a lever in the car that allowed you to change how much fuel went into the engine. And before those existed, you used to have to keep your toe on the accelerator while you put your foot on your brakes so that you could slow down while keeping your engine running.
Yes.
Before those existed, you had to crank.
Like the angle. And this is what I'm saying. And HPC systems are now, and now we have electric cars.
Yeah.
And you don't need to know any of that stuff because the technology has changed so much. And I'm beginning to wonder if we're now at that crux point where the technology of scheduling is changing, where actually users don't need that level of information.
Yes, and I'm not saying that it shouldn't be easier for them and things like that, but it probably also depends on what it is you're trying to do and what level of control you need over the thing that you're trying to do.
Should we before?
Yes.
Food's outside, and I love these discussions, but food is outside. Where did we get to? Twin.
Yeah, I'll give it a go. So yeah, it's about workflows and jobs. So yeah, we had so basically, at least for Slurm, it has very poor support for job dependencies. So if you're going to be doing like complex workflow, you'll be depending on the workflow manager to actually schedule your job, which is basically submitting little sub jobs to kind of run all of your dependencies. So yeah, I think so there's discussion about if the scheduler was a bit more aware, it should be able to kind of schedule everyone's kind of job a bit more efficiently. Anything else we talked about?
Sorry, sorry, my handwriting isn't the best, so I apologize. So like an advantage, I think an example advantage of why we want Slurm to be workflow aware is I think there's sort of two parts to that. One is you don't want to keep secrets from the scheduler. But if job dependencies are difficult to use or even brittle, which they are in Slurm, then people tend to build these monster jobs that don't fully utilize all the resources all the time because they might need a lot of GPUs soon. But right now they're preparing data and so things are going idle. And so if Slurm had known this, it might be able to do some other work with those resources. And the other thing is also goes to other things here. A lot of workflow engines are able to recover from failure. So then maybe you don't request enough memory. It's fine. Your step, the high memory step of your workflow failed. That doesn't matter. You go back and you retry. So those are like examples of what would a workflow where Slurm look like. I don't think we really talked about the responsibility split. I'm very opinionated about that, so I don't think I should.
Catch you for the beer afterwards. Sorry. Should we move on? Last table 4.
Okay, so resource modeling on constraints. So what constraints mostly shape scheduling decisions in practice? So we saw it as a user's perspective. So what is their problem with submitting jobs and so on? So one thing is, of course, the runtime of the petition, so maximum runtime. But what I saw as a big problem is memory usage. Yeah, they don't know how much memory their job uses. Yeah, I mean, who's looking at top when some tests is running or whatever to see how much memory just reads at the moment? So this was one of the things, and of course, annoying to the users is different stuff like group limits and so on. Yeah, because anybody else in the group is using the GPUs. There are thousands idling. Yeah, but I'm not allowed to use more than 2 now at the moment because everybody else is using from the same group is already using up to the limit. What do hidden constraints, topology, memory policies affect user experience?
one of these is of course the group limits. Yeah, the admins do not really publish that, and also documentations does not get really updated if they change anything to whatever they want to have. What resource types are purely model and hard to schedule today? For the only thing we could thought about was like SSD space, like part of an SSD, something like that, that's in the node, that you could use like with data movement and so on to fill directly at the start and so on. How should coupled resources, compute IO licenses be handled? I'm not sure whether we had a point for that.
That's right. It wasn't. They were just conversation starters. They don't need to all be complete.
I'm not sure, but I have good experience with job dependencies in Slurm. So we have like workflows with thousands of different steps.
We have to drink some.
And it works quite well. And so
It's parts of a heterogeneous job application.
Yeah. So one of these things is of course like the users do not know what all the options are that they could use in Slurm and so on, like this data movement stuff and so on. This is like a really big problem. But yeah, it's like an electron microscope. Yeah, it's a complex tool to use. So people should know that better. But I'm more on the opinion that the user should get less information about the cluster. Yeah, just submit what they want and we handle that for you. Yeah, so that is a different thing.
What's your team?
Yeah. What would better resource modeling look like from a user or admin perspective? Yes.
Dashboards was mentioned.
Yeah, we talked about just being able to disseminate that information to the users at least, and then they can try to make better decisions on how to use it.
Yeah, so you got with these. So they analyze the job while running and give like recommendations at the end of the job. Like the next time, maybe you use less memory because you're not using it and stuff like that. So this is a really good approach to do that. I mean, we just make the user afraid by telling them how much money they burned in energy right now at the end of a job.
Well, that's what Seams does, and we've got a similar sort of thing. It just pops up and goes into the red. And one of the feedback from the kind of performance hackathon was like, "There's a lot of red on that dashboard. There's a lot of red on there. We shouldn't have so much red. It's scary to the users." And it's like nudge factors.
Well, we don't put it red, but if there's a €250,000 for their job, then
they should know that.
Yeah, they look at it as like, ooh, that's a lot. I mean, they don't have to pay it. Yeah, but in the end, it's a good way to.
We did at one point debate whether we could send that information back to the department. And whether that might have more effect.
So something we're prototyping is instead of hard quotas, once a month we publish the entire institute's space usage on Scratch on Docker. And so it's like, well, you're working together on this big project, everyone's involved, that's fine, can be big, but then I don't know, Tom here like uses up half of Scratch. Maybe it's possible. Sorry.
Should we go and get to this? Thank you everyone very much.